This video is looking at MATLAB files which support the learning and understanding of second-order behaviours. Second-order behaviours then are covered in section 2.5 and also week 5-6 of the Rapid First course in Modelling, Dynamics and Control. Key point is we want to understand the normalised form, which includes the damping ratio. The resources here are going to focus on simple analysis and understanding of these using MATLAB tools to support that. So what does a second order system look like? So here's a generic second order model with parameters A, B and C, but it's far more common to focus our effort on this normalized form or this underdamped form where you can see we've got these parameters zeta and omega n, the damping ratio and the natural frequency. Now the key point is if we can represent a real engineering system in this form, then we can use our understanding of the generic behaviours to understand the real process behaviours. So here we focus on generic behaviours, and your job is then to translate that into a real system. MATLAB files then for second order responses. We're going to assume that viewers have already downloaded all of these files, and we split them here into two sets. There's the set here which I'm highlighting now, which we're not going to discuss explicitly in this video, so tutorial week 5, and then there's two apps for which there will be separate resources and videos, so you're far better to go straight to section 6.8 to look at those. Here we're going to focus on the two live script files which we've listed at the bottom here, which focus on analytic behaviours and then underdamping. Now a reminder, the purpose here is not to teach MATLAB, but rather to illustrate quickly where appropriate code is provided so that you can self-learn should you want to, but also to give you tools that you can use to experiment and play around so you can basically reinforce your understanding of core concepts. Let's go to the MATLAB files then. So first of all, second order models and responses, and this focuses on analytic solutions. So if we go down here to section 2, you can see here's an example of a second order model written as a maths equation, and in the grey box below you can see here's the code we used to solve it, the final solution being given in line 12, and you can see there's the solution over here written as a function of t. If you want to plot that, then an illustration of how to go about plotting that solution is given there in lines 14 to 17, and you'll see there's a couple more examples below, example 2 and example 3. Now the key point is, what if this isn't your model? What if the parameters are different? Well, I can change the parameters. That's not a 15, it's a 16. There, I've just changed it. I press run section, and there's my new solution. What if my initial condition is not 0, but let's say it's 2? So I'll put 2 there, run section, and there you can see the plot is now starting at 2 and the solution above has been updated. So it's very, very easy for you to use MATLAB tools to solve ODEs, get the correct solutions and create plots should you need them. So what about exploring the normalized form and underdamping? So this file has got two key sections. In section 2, what we're going to do is fix the natural frequency and look at what happens as we change damping. So if you look at these two figures, you can see we've got the damping ratio changes from 1 to 0.1 and the natural frequency is fixed at 1. And then in this next figure over here on the right, you can see the same variation in damping ratio, but the natural frequency is fixed at 8. Now these two figures might look pretty much identical, but if you look more carefully, you'll see the time scales are different. So as you change the natural frequency, the time scale of the behavior changes. And I can change some of these numbers if I want. So you can see the right hand figure has omega n equals 8. I can change that and say, let's make omega n equals 4. Run section, and there you see it's updated the plot. It's now done with omega n equals 4, and you'll see the time scale has changed accordingly. Now what does the section below do? The section below does it the other way round. It says let's assume that the damping ratio is fixed And here you see there's two possible values, 0.3, 0.6, and we're going to change the natural frequency. Here, values 1 to 6. Now you don't have to accept any of those values. You can go over here to the code and you can change the values to whatever you want them to be. But here I'll illustrate, for example, what if the damping ratio of 0.6 wasn't what I wanted? I wanted to try 0.5. So, oops, sorry, I put 4 there, 0.5, put that in there, run section, and it updates the plots for me. The key thing to note here is that the overshoot is the same irrespective of the choice of natural frequency. Okay, so in summary, we've demonstrated some apps and live scripts which allow students to develop an understanding of the core concepts linked to second order behaviours. And the two key parameters are the damping ratio and the natural frequency.